All right. Carbonates, phosphates, hydroxides, and sulfides are not soluble, except we go back to rule 1. If it's an ammonium or group 1 compound, always soluble from group 1. But no other carbonates, phosphates, hydroxides, or sulfides in this class are soluble. And these rules will work for everything that you need for this class. If you get to more advanced chemistry, you'll have big reference books with lots and lots and lots of charts that will let you look up when something is soluble and when something isn't soluble. Because in the end, you don't know for sure until it's experimentally determined. You don't know until you've done it, and then you can tell if it dissolved or not. So is barium sulfate soluble? No. Sulfates were soluble except barium, strontium, and lead. Sodium chloride. Yes, soluble. Sodium is a group 1 compound. All group 1 compounds are soluble. And if we look at chlorides, they're soluble except if it's silver, mercury, or lead 2. Silver nitrate, soluble or not soluble? Rule number 2, all nitrates are soluble. And this is why silver nitrate's used so much in chemistry lab. It's one of the very few silver salts that dissolves in water. So silver nitrate is probably your best all around silver reagent that will dissolve in water and chemically react. You don't ever want to spill it on yourself because it'll look like you have a terrible bruise. Silver binds with albumin proteins in the body and it turns a bluish blackish color. So if you spill silver nitrate on your skin, I mean, it's not dangerous, but it'll look like you were like beaten or something. And so we avoid that. There's a guy on YouTube who drank a bunch of silver, colloidal silver, and he turned blue because it bound up those proteins in his body. Interestingly,
how long does it take to get rid of that on your skin?
If it gets on your skin, about a week, because your skin sloughs off slowly. So it's about like a henna tattoo. It takes about a week for that to get brushed off and new skin to come up. If you take it internally, it never goes away. Your body doesn't use silver for anything, so it has no way to move it around or no way to get rid of it. You have no pumps or no channels or no carriers for it, and so you have no way to excrete it.
Blue forever?
He was blue forever, yes. This guy. So he turned blue. And again, silver is unusual in that for a heavy metal, it's not toxic. Most heavy metals are toxic to people and will poison a person. But silver doesn't. And so you can actually consume a lot of it and be healthy. Like it didn't affect his health, but it does bind albumin proteins and turn a bluish blackish color. And then if you take it internally, it's permanent because you have no machinery to excrete silver biologically. And after he died, they autopsied him, and his organs were blue too. He was blue inside and outside it. And I mean, this is like the only case that we know of that's ever happening in science. Because I mean, I think he read a health fad or something. Maybe it was on Facebook. I don't know. But like, he heard that it was healthy, and so he bought a kit. And he started electrolyzing. He'd buy silver bars and electrolyze them himself, and make this stuff himself at home and drink it. And it was apparently a pretty slow progression, so he didn't realize he was turning blue, because if you're only changing a little bit a day, and you see yourself in the mirror a day, you don't notice super gradual changes. But it wasn't until like people that hadn't seen him in a while saw him and all of a sudden realized that he had turned blue.
He looks like the kind of guy that drinks that stuff.
Fair enough. Silver hydroxide. Hydroxides are not soluble, except, go back to rule 1, ammonium and group 1. But that's not silver. So silver's hydroxide will not be soluble. Ammonium carbonate, soluble or not soluble? Soluble. Back to rule 1. All ammonium salts are soluble. Like dissolves like. Polar solvents dissolve polar compounds. Nonpolar solvents dissolve nonpolar compounds. And so gasoline will dissolve grease pretty easily, whereas water will dissolve the salt pretty easily. Water, or like dissolves like. It's a general rule of solubility. So carbon tetrachloride is completely nonpolar. It dissolves well into hexanes. Whereas water would not dissolve into hexanes because one's polar and one's not polar. Ionic compound solubility in polar solvents. Several ionic compounds dissolve in water due to strong ion dipole forces. Remember, water had a partial negative and a partial positive. So it has this negative side here on the oxygen, and it has this positive side that's centered between the two hydrogens. Because of that negative and positive, here is dissolving table salt, sodium chloride. The negatives of the water molecules bind the Na pluses, and the positives of the water molecules bind the Cl minuses. And they circle around the ion and solvate it. Something is not dissolved until it has a shell of hydration. That's a shell of water that collects around it, and then it's stuck to it. The shell of water moves with the ion. So as the ion moves around, so does the shell of water. Well, they don't show a good picture there, but you see it here. That's really important in biology. It's how the body can tell sodium from potassium. Because that was a question in biology. Sodium and potassium are both +1. Sodium's a lot smaller than potassium. Why doesn't it go through a potassium channel? And the difference there is in the shell of hydration. Because sodium's a lot smaller, but it still has a +1 charge like potassium, the charge density on a sodium is higher. And so it has a much bigger shell of water around it than potassium does. And your body differentiates between sodiums and potassiums by how thick that shell of water around them is. And so it can tell which one is which. Because they both end up being about the same size when you add their shell of water. And so one has a much thicker shell of water, and the body recognizes that sodium. And so the waters around these ions are really important for biological function, actually. Temperature and solubility. Blue is gases, red are solids. You'll notice in general, as the temperature goes up, solids get more soluble. You'll also notice, if you look at the two blue lines, as temperatures go up, gases get less soluble. And that's why the pop will explode in the hot temperature car. As it gets hotter and hotter, the gases escape the liquid and want to burst away. So as the temperature gets bigger, salts get more soluble. There's more kinetic energy, which means there's more interactions with the liquids and the solids, making it easier to solvate. Gases, however, become less soluble because once they get this energy, the gas can escape from the liquid. And so the gases actually start escaping and bubbling out of the liquid. So they become less soluble because they have the energy to escape. Whereas a solid can't escape. And so as it gets more energy, it starts dissolving more, actually. And so the reason that gas solubility goes down instead of up is because the gas has the ability to escape away from the liquid and bubble away, which is what happens. Pressure. The external pressure does not affect the solubility of liquids or solids. So external pressure would not affect dissolving sugar into water, or it would not affect dissolving ethylene glycol into water. It does affect dissolving gases. It's proportional. If you double the external pressure, you'll double how much gas dissolves. So external pressure, while it does not affect the solubility of liquids or solids, it affects gas solubility tremendously. And it's proportional. If we times the atmosphere by 100, we times by 100 what dissolves. And so they make soda pop. It's done under really high pressure conditions. So a lot of gas dissolves in. That way when you open a soda pop under normal conditions, the gas starts bubbling out because it's at a lower pressure than it was bottled at. And this can become a problem with scuba divers. The deeper you go, every 12 feet into the water you dive down, you have another atmosphere of pressure on your body. And the more pressure on your body, that affects gas solubility, the more gases dissolve into your blood. And so if you're really deep down, a lot of nitrogen gas that you breathe in is dissolving into your blood. If somebody comes up too fast, it'll precipitate out and it'll form bubbles in their blood, which is really bad. And they call that the bends. It can range anywhere from extremely painful to actually fatal and kill someone, because your circulatory system is not meant to have bubbles in it. And so if you're using normal air, you've got to come up slowly. If somebody's afraid they're going to see a shark and freak out and come screaming up, you want to use helium air, which is just helium and oxygen. And that works a lot better, because whereas nitrogen is extremely soluble in blood, helium's not. And so even in really deep pressure, there's not a whole lot of helium dissolved in the blood. It's more expensive, but it's worth the charge if you're afraid that you're going to see a shark and freak out and scream for the top, which can happen.